Okay, so this is our 8th FRQ. We're going to need to know a few things. We're going to need to know conservation of charge. When a charge capacitor is connected to another, the total charge is conserved, redistributed between them. Steady state potentials. Once it reaches equilibrium, after a long time, capacitors connected in parallel must have the same potential difference. And then our formulas are going to be Q equals CV or UC if you substitute for V, and then our time constant is RC. So now we're going to draw for problem A. So we are going to draw this battery, and then it's going to go into of our switch. And then capacitor 1 would be connected to the top here. And then so this would be only charges, so then it would be in discharge. So this would be position 1, and then when in position 2, this should be resistor R. And then we're going to have C2. And that should be our thing. And when this is closed, it would then discharge through the capacitor through C2. Okay, so that's going to be our little schematic. Let's move to B. Label each box to indicate which graph corresponds to. So this one would be C2, this one would be C1. So this would be C2 since, or yes. So C2 starts at 0 and then increases exponentially to it's going to reach that asymptote. So that's going to be C2 because it was initially uncharged. C1 is going to be the exact opposite because it was initially charged. And then it's just going to exponentially decay. Okay. C. 2 parts. Calculate the following charges. Okay. Well, we know Q total. And then at final state, they're going to reach a common voltage. Be total. It's going to be 24 microcoulomb because 3 volts. Okay, well, so for the charges Q1 and Q2, well then, so we found our V, so Q1 just be C1, 2 times 3, and then Q2 is just going to be 6, or C2 times 3, it's 18, and we know that it's going to be 3 for both because after steady state, they are going to share the same voltage. So we're going to get 6 and 18. And then the potential difference is V1, V2. Oh, those are both 3. That's what I just said after, since they are steady state. Same. Okay, now, right, but calculate the total energy dissipated in resistor R during the time C1 changes. Oh, well, that would just, oops, U initial, that's going to be, we know it's 1/2 CV squared, so 1/2, 2, that would just be 144 microjoules. And then U final 8 times 3V squared, because that's what we have at the end. And then that's just going to be 4 times 9, yeah, 36. And then we're just going to subtract the 2, and that 108. So that's D. And then E. Okay. Write, but do not solve. Okay, well, we could use the loop rule. So, no. So it'd be voltage across everything. So it'd be Q1, so first voltage, minus pi R minus and then we know I equals dq over dt. So our differential equation be Q1 over C1 minus R dq2 over dt minus Q2 over CT. C2, excuse me. And then that will be our differential equation because we have this. And then, yeah, and then we don't have to solve, but we would match them all together and then we'd get a differential equation. And then calculate the time constant associated with the charge. Well, for that, we'd have to calculate equivalent capacitance. And that would be adding so it'd be 1/2 plus 1/6, 2/12 plus 6/12 equals 8/12. And that's how we add capacitors in series. So 8/12, that's 1 over RC equivalent. So then that would mean C equivalent equals 12 over 8. And then, so that's the same as 1.5. Makes it easier. And then our time constant, if that's our C, our time constant is RC, 1,000 ohms times 1.5. That'd be this is 1.5. Let's just look that up because it's 1.5. It's 10 to the negative 6. 0.0015 seconds. That's our answer. So that's number 8. And I'll see you in the next one.